No, okay, let's go on. Next, I go to Fubini's theorem. So consider in our square some set A. And A is a measurable set. So this is X, this is Y, and let us define this set AX Y such that XY in A. It is the section. So this is X, and we project intersection of this line X equal constant with set A onto the Y-axis. And correspondingly, AY equidistant X such that XY in A. And consider the following function. F of X equals measure of AX. Measure of this set. Yeah? No, measure in the y-axis. So let me denote measure in the x direction is mu1 and here mu2. So it is mu2 of AX. Yeah. And this is the slice of the size of the slice of this set, and we write the claim is the following. First theorem, it is not Fubini, it is a preparation to Fubini. Lambda of A equals integral, no, down in here integral from 0 to 1, mu2 of AX d mu1 of X. So we take the measure of this slice and integrate it over X. So in fact, this is an ancient principle which was known by Archimedes. In a new time it was called Cavalieri principle. So to find the area of some domain, you have to slice into it into infinitesimally thin strips and find the sum of the areas of these strips. So nothing unusual. So unusual thing is that the set A can be complicated. No, at least uh, um, it can be any Borel set. So it is already maybe transcendentally complicated. So it is far from obvious. So we have to prove this theorem. We have to prove the following thing. First, fx is defined for almost all x. Ax is measurable. Second, the function fx, f of x, is measurable. And third, no, the equality itself, to prove this equality. And so to this end, I use the following lemma. Let A be measurable set here in the square. A measurable set. Then there exists B1, B2, and so on, also in M bar, such that measure lambda of B Bn delta A is less than 1 over n, one thing, and Bn equals union B and K over K, such that B and K in M, so they are elementary sets. Yeah. So we have to prove this. No, first of all, if proof so if the set A is measurable, then the following is true. For any n, there exists. A is measurable. Measurable I denoted by t. And b1, b2, and so on is in M. For any n, there exists bn in M bar such that lambda star of a delta bn less than 1 over n. It is the definition of measurable set. So bn we have. And now bn is union of countable number of elementary sets, or in the same countable number of rectangles, because each elementary set is a union of finite number of rectangles. Yeah. So Bn equals union. Let me write Q N K. K rectangles. Yeah. So we have that's it. So the lemma is proved. It is simply by definition. And now let us consider B equals intersection of all Bn. So B is smaller than all Bn. This means that lambda star of B delta A equals 0, because for any Bn it is less than 1 over n. Uh, 1 minute. No, let me take, I'm sorry. Let me write the following thing. Bn contain A and lambda Bn minus A. Bn minus A, let us think. So Bn form a general decreasing sequence, and if you take intersection of Bn, then the upper measure of it is 0. So this is the set B, and Bn is union of B of Q and K. And Q and K intersect Q and J is also empty over k. So we have this from 1 to infinity. Very good. And now consider the following thing. Here is, now I return to our formulation of our theory. Consider a characteristic function of our set A and a characteristic function of our set A equals infimum of characteristic function of the set intersection of the set Bn equals intersection of Bk k from 1 to n. So we consider these sets, and this goes because the set Bn plus n plus 1 is in Bn. Yeah, no, this or at most this. This means that this is decreasing sequence of functions, characteristic functions. And characteristic function of Bn equals Bn is the union supremum of simply sum, because they are non-overlapping, some characteristic function of Q and K, sum over K. Yeah. Okay. And now consider the function. So first of all, lambda of A equals integral characteristic function A of xy d lambda. Yes? First of all. No, by definition of integral, here integral is integral of simple function which takes values 0 and 1. So it is by definition, and integral characteristic function A d lambda, and we have the function Bn, the sets Bn goes down, so it is monotonically decreasing or non-increasing sequence of function. So it equals to limit when n goes to infinity, integral integral kappa bn d lambda. Yeah. So first of all, this, and each bn is the bn is sum of these characteristic function of bn is a sum of countable number of characteristic function of rectangles. Yeah, and so by if you consider partial sums from say k from 1 to some k capital, yes, and then k capital grows, then this function grows, yes, and so it is mm, uh, limit n to integral sum kappa q n k over k d lambda. Yeah. Uh, and the limit is also a measurable function. Yeah, and the integral of the sum is sum of integrals. One moment. Um, Now consider the function, say it was the function f of x equals uh, the measure mu 2 of the set A intersection with x um, uh, the set xy set y such that xy in A, yeah, it is f x. First of all, the function, characteristic function of the set y uh, characteristic function of the set x, y in A and as a of y, let us consider the set say alpha x equals the set xy, a set y such that xy in A. Yeah, and characteristic function of the alpha x, it is a function of y, equals, and let me note beta xn equals the set of y such that xy in Bn, Bn here. And the x here alpha x of y, it is infimum. Here beta xn of y. Yes, because this function is decreasing. But if you have a decreasing sequence of measurable functions on the line, it will be, it has a limit almost everywhere, no, everywhere, at every point, and this limit is a measurable function. Measurable function. Whew. Okay, so we have this thing, and now let me start from the following thing. If you consider a rectangle R, yeah, and consider A equals R, and consider the length of intersection of this rectangle with the line x equal constant, then we have fx equal, let's say it is a, b, it is c, d, equals d minus c if a y less than a less than x less than b, and 0 otherwise. Yes? So fx is here. And we can have that integral fx d mu 1, yeah, equals simply b minus a d minus c equals lambda of r. Yeah, so for elementary rectangle, we have that integral this fx is exactly the area of this rectangle. And now for our more advanced set, we can find that if, say, Bn equals intersection bk, k from 1 to n, yes, and bk in M bar, so they are countable unions of rectangles, then bk intersection is also countable union of non-intersecting rectangles. And so this means that Bn is union of Q and K, countable union, and chi Bn equals sum chi Q and K. Yes, and integral. First of all, integral chi Bn over domain x is constant d mu2 of y equals, so what is this? We had some rectangles which do not intersect. This vertical line x is constant. Some do intersect. Yes, and we have to take only the rectangles which do intersect. It will be some subsequence of these rectangles. Each of them will give you some characteristic function, and for different rectangles these characteristic functions do not overlap because rectangles do not overlap. Yes, and this means that the sequence of characteristic functions, no, the sum, sequence of partial sum of this series of characteristic functions on this line is a series or sum of the series of growing sequence of measurable functions, which is a measurable function, and it's even bounded by all our theorems. So, first of all, chi b n of y of xy as a function of y is measurable for any x. First thing. Second thing, that the function bn themselves are decreasing. Yeah. So this I would say that if you consider just this function and substitute it to our formula, then you see that this works for every rectangle, every such rectangle, and so it is true for one moment. Let me return a little bit back. A measurable set. The theorem, there exists a set B 1 containing B2 containing A, such that the upper measure of Bn minus A less than 1 over n, so goes to 0. Bn is intersection Bk, k from 1 to n. Bn equals union q kn, k from 1 to infinity. Q kn, kn rectangle. Q kn q jn. So here I write all what I have. Then chi, a characteristic function Bn equal sum chi q kn, k from 1 to infinity. First of all, sum of this characteristic function. And one moment. I don't need this because they already go decrease, so it doesn't change. Bn. So Bn. Bn decreasing, so this means chi Bn equals I'm sorry, B equals intersection of Bn, yeah, and from 1 to infinity, and chi B equals infimum chi Bn equals infimum over n. Let me write supremum sum chi q kn k from 1 to m over m. Yeah, like this. And what I wanted to say that if you have a sequence of positive functions like this, and consider the supremum of them, and this sum, if you take it sum as a function of m, it is the increasing system of function, and this supremum of this increasing system of function, but it is bounded by 1 because it's characteristic function. And so this means that this is first measurable function on every measurable function in the square, and its restriction on any vertical line is also measurable function, because after all it is the sum of characteristic functions of intervals. Yeah, which intervals do not intersect. Yes, and now I take this function, which is measurable, and take infimum of these functions when n other index decreases. And this infimum also is a measurable function by the same thing. Now, let us consider this. It is finite set. Lambda of union q k n k from 1 to m. For each of these rectangles, we have the formula that the area of a rectangle is the integral of the characteristic function. Along, we take the integral characteristic function along the vertical line, x is constant, and then integrate it over the second line. So it is sum or integral sum characteristic function q k n k from 1 to m of x y d mu 2 integral d mu 1. So this holds for one rectangle, and this holds for a finite number of rectangles. Now I write, because this function, which is here, is increasing for when m goes to infinity and grows, we have so by the monotone convergence theorem. So if a sequence of function monotonically non-increasing and goes to the limit, then integral of this limit function is equal to limit of integrals. Integral of sum k from 1 to infinity chi q k n of x y d mu 2 d mu, let me write d mu of y times d mu of x, and this is equal to integral so what is this sum? It is characteristic function of the set Bn chi Bn of xy d mu y d mu x. Yeah. Now Bn chi Bn is decreasing because this is decreasing system of sequence of sets. Yeah. So somewhere this characteristic function changes from 1 to 0, but cannot change from 0 to 1. And by the same theorem, uh, and decreasing to B, KB. B is intersection of Bn. By the same theorem, it goes both for increasing and decreasing. Theorem is here, monotone convergence theorem. Integral chi uh, uh, it is equal lambda of Bn. Uh, integral integral chi Bn d mu y d mu x decreases to integral integral chi b d mu y d mu x, and which is lambda of b. Yeah. So what we achieved, we found a set B in T. B has a special structure, is an intersection of countable number of elementary of the sets of M bar. Yeah, so it is very non generic set of the sigma algebra, such that there exists Bt, such that lambda star of B of A minus Bt minus B equals 0. Yeah, that's it. And lambda of B equals integral T chi B of xy d mu y d mu x. Whew, that's it. So in fact, we are not working now with the set A, but with set B. But the set B differs from the set A by a set whose external measure is 0. Yeah. So we are working with a 0 set. They differ. So this means that all the from the viewpoint of measure theory, there is no difference between these two sets. They are differ by only the set of measure 0. Yes. So I have to repeat here that the algebra of Lebesgue sets is extension of Borel sets by the sets of measure 0 and all subsets of measure 0, external measure 0. So there can be not Borel sets, but they are included in some measurable sets of measure zero, so it is they are negligible. So this set B is goes instead of set A. But for example, all the functions can be defined on B, and it makes no difference in respect to integration of them, because the difference will be zero anyway. Okay, and now let me assume that this is proved. And now I formulate for B theorem. Suppose f of xy is lambda measurable and integrable. So if you have a measurable function defined in on some sigma algebra, then we can integrate it. Define the Lebesgue integration does work. And integrable means that integral of module f d lambda, or integral over E, is finite. Yeah. Then integral f d lambda equals integral from 0 to 1, for example, integral from 0 to 1 f x y d mu y d mu x. Now equals integral from 0 to 1, integral from 0 to 1 f x y d mu x d mu y. So we can integrate in both orders, and this gives us the usual tool in calculus, that double integral can be found as a iterated integral. No, okay, so proof. So let me give the following proof. First, suppose f(x) more or equal than 0. Now let us approximate this solution, this function from below, by a simple function. Define fn of x equals k over n if I need more space. Fnx equals k over n if k over n less or equal than fx less than k plus 1 over n, and k equal 0 uh, up to n square, yeah, for example, and say 0 otherwise. No, it means 0 when fx more than n, yeah, or maybe no, okay, n. If fx more equal than n. Yes. So consider this function. Then consider the sets. Uh, Set A, K, N, the set X, Y, such that uh, uh, K over N less or equal than F of X, Y less than K plus 1 over N. Yeah. So they have these sets A, K, N, and then we write F N X, Y equals sum uh, the function K over N, characteristic function of the set AKN of XY. Yeah. And then for K equals N square, we have this. Yes. No, it goes. It is for K equal less or equal less than K less than N square, and here fx more equal than N if K equal N square. Then integral Fn d lambda over the whole square equals sum by Lebesgue integral sum K over N lambda of characteristic function of on A K N. K from 1 to N, from 0, so that it can be 0. K from 0 to N. So this is the integral, and now let us write this formula for lambda. Equals sum K from 0 to N integral K over N integral characteristic function A K N of x y d mu y d mu x. Let me write it Kn here. K over N equals integral no, it is finite sum. Integral uh, uh, sum k from 0 to n square, uh, k over n chi I k n of x y d mu y d mu x, and this is the same characteristic the same function fn. Yeah, it is characteristic function because it is k over n on different sets. So this is the same as this. Equals integral uh, integral fn xy d mu y d mu x. Okay, and now uh, integral fn d lambda goes to integral f d lambda by the monotone and bounded, no, bound, how it is called, um, uh, dominated convergence theorem. Because Fn are first growing when n grows, and second they are bounded by f, which is integrable. So, and this means that this, one moment, integral fn, no, in fact, fn between 0 and 1, either 0 or 1. So this integral can be, no, it is k over n, so it is not more than k over n. So this means that integral fn of xy d mu y also grows to integral f xy d mu y by the same theorem. Yes, it grows. And the total integral, which is equal to this integral fn d mu y d mu x equals to integral fn d lambda. This integral goes to the finite limit, so this integral fn of xy d mu y d mu integral d mu x goes again growing to the integral again f d lambda. No, okay, so this we go to the limit in this integral, go to the limit in this integral, both parts, both times we use the same theorem on the bounded convergence, because this integral is bounded by n. Yes, it can be more than it, so it is converges to the limit. And then, as a result, this integral goes to this limit yes, so No, by the same theorem. That we have a sequence of functions which is bounded by an integrable function. That's it. That's it. So we proved the theorem. It is not the whole theorem because we proved it only for positive function. But now we do the usual trick. We write f x y equals f plus module f over 2 plus f minus module f over 2 equals f plus of xy minus f minus of xy. So f plus of xy equals f plus module f over 2 more or equal 0. Yes? No, if f is positive, it equals f. If it's negative, it is 0. F minus xy also more equal than 0. It is minus f if it is negative, and f it is positive. Yes, and we can prove it for this and for this, and then no, because they have non-overlapping supporting set where they are different from 0, so we can find use this Fubini theorem for separately for f plus and f minus, and then subtract them. That's it. So let's finish. If something is not clear, I will clarify next time. For now, let's finish. Bye.